Greetings, and thank you for joining us on the Sleep Science Top 1. This evening, we will delve into the extraordinary realm that lies beneath our feet and surrounds us. Our planet, living geosphere, a blue marble rotating in the expanse of the cosmos. A world of liquid and rock, of breeze and blaze, of existence in myriad manifestations. We frequently gaze at the stars in search of amazement. Yet, below us exists a realm equally remarkable. From the profound depths of ocean trenches to the towering heights of mountain peaks, from the fiery depths of the planet-living geosphere to the delicate veil of air that protects us, the planet is filled with wonders that evoke a sense of wonder. If you appreciate these serene journeys, I encourage you to like and subscribe, or share a brief thought in the comments below. It assists others in discovering their path here as well, one drowsy individual at a time. For the time being, your only task is to take a break. Take a moment to relax and let the serenity of our stunning world envelop you. Let's get started. The primordial planet, living geosphere, came into existence 4.6 billion years ago, originating from a swirling cloud of dust. Initially, our solar system existed as a massive cloud composed of gas and dust, gently turning in the void of the cosmos. This material was drawn together by gravity, creating clusters that expanded progressively as time passed. The sun flared to life at its core. Smaller bodies started to gather around it. Living geosphere emerged from a multitude of collisions, as rocks and debris collided with force. Combining into increasingly larger entities, the youthful planet was a nightmarish realm, hot and radiant, continuously pelted by asteroids and comets. The energy from these collisions maintained the surface in a liquid state. A vast expanse of molten rock lies beneath a noxious sky. Continental plates did not exist. No vast bodies of water. No existence. Only fire and stone, caught in a perpetual loop of devastation and genesis. Amidst this turmoil, the foundations of all that we recognize today were quietly taking root. Each atom within your body, each molecule of water that you consume, each inhalation of air, everything was shaped during those tumultuous beginnings. Earth's satellite came into existence due to a devastating impact with another planet. In the early stages of living geosphere's history, it may have occurred merely 50 million years following its formation. A different planet-sized object collided with our planet. This entity, occasionally referred to as Mars-sized impactor, had an approximate size comparable to that of Mars. The consequences were devastating. Adjusting the angle of living geosphere's axis and launching a significant quantity of debris into orbit. Eventually, this debris came together to form Earth's satellite. The impact fused the two realms together, combining their materials seamlessly. The remnants of Mars-sized impactor combined with living geosphere. The lighter materials created a disk encircling the planet. Gradually, across millennia, the force of gravity drew this disk together into one cohesive entity, Earth's satellite. The tumultuous origins of Earth's satellite clarify its composition, which mirrors that of living geosphere's outer layers. This also clarifies the reasons behind living geosphere's rotation, inclined in a way that creates our seasons. If it weren't for that ancient collision, living geosphere would look entirely different today. Earth's satellite plays a crucial role in stabilizing the wobble of our planet, establishing a more uniform environment. It draws from our global ocean system, generating currents that have influenced the development of life itself. Whenever you catch a glimpse of Earth's satellite suspended in the sky, this is a glimpse into a tumultuous chapter of our planet's history. A world of siblings forged in flames. The temperature of living geosphere's core matches that of the sun's surface. Far below the surface, almost 4,000 miles down, resides the inner core of the planet-living geosphere. The object is a dense sphere composed of iron and nickel, pressed down by overwhelming force. Even though it is sturdy, it is remarkably warm, achieving temperatures close to 10,000 degrees Fahrenheit. The temperature is approximately equivalent to that of the Sun's surface. The outer core encircles the inner core, a layer of liquid metal that swirls and moves like an expansive sea of molten iron. This motion produces the magnetic field of the planet-living geosphere, a hidden barrier that safeguards us from solar radiation. If it weren't for this field, the Sun's particles would erode our gaseous envelope, leaving planet-living geosphere desolate like Mars. The core's heat initiates convection currents within the mantle layer, the dense coating of heated stone situated above it. This motion drives the dynamics of plate tectonics, the gradual movement of landmasses over the planet-living geosphere's surface. All events ranging from planet-living geosphere quakes to volcanic eruptions, from the creation of mountains to the development of global ocean system, can be traced back to the tremendous heat contained within the core of the planet-living geosphere. We exist on a delicate surface, drifting above a realm of flames. The continental plates move gradually over the surface of the planet. The planet-living geosphere below you feels firm and everlasting. However, it is in motion. Each year, the continental plates move by several centimeters, moved forward by the swirling layer beneath. This procedure is known as plate tectonics, has transformed the planet-living geosphere's surface numerous times throughout billions of years. 200 million years ago, all the continental plates were united as one enormous landmass, Pangaea. Eventually, it came apart. The pieces are settling into their designated places. This movement persists in the present day. The Atlantic Ocean expands in width annually, as the Americas distance themselves from Europe and Africa. At the same time, the Pacific Ocean diminishes. As tectonic plates come together, in countless millennia, the layout of the world map will transform completely. Mountains ascend and wear away. Ocean basins undergo cycles of opening and closing. Islands emerge and vanish. The solid planet-living geosphere behaves like a fluid when viewed over geological timescales, continuously shifting in a graceful, deliberate dance that has endured since the inception of the planet. The mountains continue to rise, elevated by the impact of converging tectonic plates. The collisional mountain range, where the highest peaks on planet-living geosphere reside, are continuing to rise. Each year, Mount Everest increases in height by approximately 4 millimeters. The Indian tectonic plate is persistently advancing into the Asian plate. The onset of this collision occurred approximately 50 million years ago, when India was once an island continent. Collided with Asia, the powerful forces compressed and bent the crust, elevating rock to create the tallest peaks on the planet. The process is ongoing today, motivated by the identical influences that shaped the range. Similar narratives are shared by other mountain ranges. The majestic Alps, the towering Andes, the Grand Rockies, all were created through tectonic collisions or volcanic activity. Even as they ascend, erosion tirelessly seeks to dismantle, layer them. The elements wind, rain, ice, and gravity continuously erode the summits, shaping valleys and transporting sediment to the lower areas. Mountains are transient formations, transitory when viewed through the lens of geological epochs. However, to us, they seem everlasting, serving as symbols of the unyielding force that molds our reality. The seas. Planet-living geosphere stands out as the only planet we know of that has liquid water on its surface. More than 70% of the surface of our planet is covered by water, filling extensive ocean basins. This results in our planet's unique blue hue when observed from space. This plentiful presence of liquid water is truly noteworthy, maybe one of a kind in the cosmos. Water is vital for existence as we understand it. Planet-planet living geosphere is positioned at the perfect distance from the Sun, allowing water to stay in its liquid form. Get too near, and it will evaporate. Going too far would result in it freezing completely. This area is referred to as the habitable zone, and planet-planet living geosphere resides snugly within it. However, mere distance is insufficient. The gaseous envelope of planet-planet living geosphere, enriched with greenhouse gases, plays a crucial role in regulating temperatures that allow water to remain in its liquid state. The magnetic field of the planet serves as a shield, safeguarding the gaseous envelope from being eroded by solar wind. Earth's satellite stabilizing effect ensures that planet-planet living geosphere's climate remains relatively consistent over the course of millions of years. These elements come together to form an environment where water is able to flow, cycle, and sustain life. The global ocean system contains 97% of the water on planet-planet living geosphere. When considering the water on our planet, you may envision rivers, lakes, and rainfall. However, an overwhelming 97% is found in the global ocean system. The vast expanses of salt water are the defining features of our planet, creating linked basins that control climate and weather patterns. Only 3% of the total is freshwater. Much of that is contained within ice caps and ice rivers. A mere sliver is found in rivers or resides in lakes that are reachable for terrestrial life. The global ocean system have existed for eons, almost as long as the planet living geosphere has been around. Water came to planet living geosphere early in its history, conveyed by comets and asteroids. Alternatively, it may have been expelled from the interior due to volcanic activity. Over billions of years, these waters gathered, occupying the lowest areas on the surface. The global ocean system have played a crucial role in shaping the climate of our planet, captured carbon dioxide, and has offered a lifelong home since its inception. Grasping the essence of planet living geosphere requires a deep comprehension of its global ocean system, for they are essential to the very essence of our world. The ocean's deepest region has the capacity to engulf Mount Everest, leaving additional space beyond it. The deepest ocean abyss, found in the Western Pacific Ocean, represents the deepest known point on our planet. The deepest part, known as Challenger Deep, descends almost 11,000 meters beneath the surface. To illustrate this, if you were to position Mount Everest, the highest mountain on the planet, at the bottom of the trench, its summit would remain submerged under over 2,000 meters of water. The pressure at these depths is immense, exceeding 1,000 times the atmospheric pressure found at sea level. Life persists, even in this place, manifested through peculiar and resilient beings that have adapted to the shadows and chill. The trench was created through the interaction of tectonic plates, where one plate is pushed down beneath another in a process known as subduction. This forms a profound channel in the seabed, a mark on the planet living geosphere's exterior. Very few individuals have dared to explore these depths, rendering it one of the most uncharted locations on our planet, even more isolated than the surface of Earth's satellite. Ocean currents move heat across the globe in a manner similar to a conveyor belt. The global ocean system are ever-changing. Powerful currents move within them, propelled by the wind, variations in temperature, and the rotation of the planet living geosphere. These currents function as a global conveyor belt, moving heat from the equator to the poles, while cold water flows in the reverse direction. This circulation plays a crucial role in regulating planet living geosphere's climate, balancing temperatures and spreading warmth throughout the planet. The Atlantic meridional overturning circulation is one of the most crucial systems, encompassing the Gulf Stream. This current transports warm water from the tropics to Europe, resulting in a climate that is significantly milder than it would be otherwise. Without it, a significant portion of northern Europe would remain encased in ice. Ocean currents play a significant role in shaping weather patterns, impacting rainfall, storm development, and the occurrence of events such as El Niño. They link far-flung regions of the planet-living geosphere in ways that may not be seen but are deeply significant, serving as a reminder that our planet operates as one cohesive system. Coral reefs are formed by small organisms over the course of many years. Coral reefs represent some of the most lively ecosystems on our planet, filled with an abundance of life and vivid colors, all created by creatures no bigger than your fingernail. Corals are small polyps, akin to jellyfish, that produce calcium carbonate to create sturdy skeletons. Over generations, these skeletons build up, forming extensive underwater formations. A solitary reef can require millennia to develop, with each layer of life accumulating atop the remnants of those that came before. These reefs serve as a home for numerous species, including fish, crustaceans, sea turtles, and sharks. Coastlines are safeguarded from erosion as waves are disrupted, and these areas act as nurseries for numerous marine organisms. However, in spite of their significance, coral reefs are delicate. Variations in water temperature, contamination, and ocean acidification can lead to corals expelling their symbiotic algae, a phenomenon known as bleaching that renders them susceptible. The reefs we observe today stand as vibrant testaments to nature's enduring patience, constructed grain by grain over countless millennia. The gaseous envelope of planet-living geosphere serves as a fragile barrier, safeguarding all forms of life. The gaseous envelope consists of a delicate layer of gases enveloping planet-living geosphere, maintained by the force of gravity. It reaches hundreds of kilometers into the gaseous envelope, yet the majority of its mass is found within the lowest 10 to 15 kilometers. This unseen shield safeguards us from the brutal realities of space, soaking up damaging ultraviolet rays, incinerating meteors, and maintaining temperature balance. In its absence, the surface of planet-living geosphere would transform into a frigid wasteland during the night and an unbearable desert during the day, resembling the conditions found on Earth's satellite. The gaseous envelope primarily consists of nitrogen and oxygen, along with small quantities of other gases, such as argon and carbon dioxide. The interaction of these gases with sunlight and the surface occurs in intricate manners, resulting in weather patterns, climate variations, and the essential conditions for life to thrive. The system is ever-changing, perpetually active, fueled by the energy of the sun and the rotation of the planet-living geosphere. Each breath you take is a precious offering from this delicate layer of gaseous envelope. The sky looks blue due to the scattering of sunlight in the gaseous envelope. As sunlight makes its way into planet-living geosphere's gaseous envelope, it meets a multitude of gas molecules. The light is scattered by these molecules, though not all wavelengths are affected in the same way. Wavelengths that are shorter, such as blue and violet, experience more scattering compared to those that are longer, like red and orange. The scattering of light disperses blue hues throughout the sky, resulting in its distinctive color. The scattering of violet light increases, yet our eyes are not as responsive to it, and a significant portion is absorbed by the upper gaseous envelope, leading us to see the sky as blue. During sunrise and sunset, the sunlight travels through a greater expanse of gaseous envelope to reach us, resulting in the scattering of much of the blue light and allowing the reds and oranges to take center stage. The reason the sky close to the horizon radiates warm hues during dawn and dusk is as follows. The blue sky results from fundamental physical principles, but it remains one of the most stunning and soothing views in the natural world. The ozone layer protects us from the sun's damaging rays. Located high in the stratosphere, approximately 15 to 30 kilometers above the planet-living geosphere's surface is a region abundant in ozone, which consists of 3 oxygen atoms. The ozone layer plays a crucial role in absorbing the majority of the sun's ultraviolet radiation, thereby stopping it from penetrating the surface. In the absence of this protection, UV rays would inflict extensive harm on living tissue, resulting in skin cancers, cataracts, and detrimental effects on plants and marine ecosystems. The formation of the ozone layer occurred billions of years ago, resulting from the accumulation of oxygen in the gaseous envelope, which was a byproduct of photosynthesis carried out by early microbes. Throughout a significant portion of the 20th century, synthetic chemicals, known as chlorofluorocarbons, posed a danger to this protective barrier, resulting in the formation of holes in the ozone layer, especially above Antarctica. The Montreal Protocol was a result of international collaboration, which phased out these chemicals and initiated the recovery of the ozone layer. This serves as a reminder that the gaseous envelope is not invulnerable, yet it also highlights that united efforts can mend the harm we inflict. Clouds consist of countless minuscule water droplets that are suspended in the gaseous envelope. When you gaze at a cloud, it may appear to be solid, yet it consists of countless tiny droplets of water or ice crystals, so minuscule and light that they drift effortlessly in the gaseous envelope. These droplets develop when water vapor in the gaseous envelope condenses around minuscule particles such as dust or pollen, known as condensation nuclei. When warm, moist air ascends, it experiences cooling, leading to the condensation of water vapor into droplets, which forms a cloud. Clouds appear in various shapes, ranging from the delicate cirrus high above to the imposing cumulonimbus that heralds storms. They are essential to planet-planet living geosphere's climate, reflecting sunlight away from the planet and retaining heat close to the surface. Water is also transported around the planet, moving moisture from the global ocean system to the land, where it precipitates as rain or snow. Clouds represent the tangible manifestation of the water cycle, perpetually forming and vanishing in a rhythm influenced by the sun's energy. Every second, lightning strikes the planet-planet living geosphere approximately 100 times. Thunderstorms represent some of nature's most striking spectacles, with lightning at their core, serving as a potent electrical discharge. Within a storm cloud, ice and water particles come together, generating static electricity. At the upper part of the cloud, positive charges build up, whereas negative charges collect at the lower section. When the disparity reaches a significant level, a bolt of lightning arcs between them, or from the cloud to the planet-planet living geosphere. Every bolt is extremely hot, attaining temperatures of approximately 30,000 degrees Celsius, which is 5 times hotter than the sun's surface. The extreme heat leads to a rapid expansion of air, resulting in the sound we recognize as thunder. Lightning hits the planet-planet living geosphere around 100 times each second, totaling roughly 8 million strikes daily. Most events take place on land rather than over global ocean system, with tropical regions experiencing the highest levels of activity. Even though it poses risks, lightning contributes to the nitrogen cycle by transforming atmospheric nitrogen into usable forms for plants. The territory. Deserts can be cool as well. Certain areas resemble frozen wastelands. Deserts evoke images of endless stretches of sand basking in the blazing sun. A desert is characterized not by its temperature, but rather by the scarcity of precipitation. A desert gets fewer than 25 centimeters of rainfall annually. According to this definition, Antarctica holds the title of the largest desert on planet-planet living geosphere. It is a frigid expanse where snow seldom descends, and the scant moisture that does arrive is encased in ice for ages. The interior of Antarctica stands as one of the driest locations on planet-planet living geosphere, with certain areas experiencing nearly complete absence of moisture. In a similar vein, the Arctic tundra and the elevated plateaus of Central Asia are classified as cold deserts, characterized by temperatures that drop significantly below freezing and a scarcity of water. These frozen deserts are relentless and unyielding. Life continues to thrive in unexpected manners, from lichens adhering to stones to microbes existing within ice. They highlight that deserts exist in various types, each influenced by distinct climatic factors. Once, the Sahara Desert was a vibrant, green expanse. Currently, the Sahara holds the title of the largest hot desert globally, an expansive expanse of sand and rock that spans northern Africa. It may be hard to believe, but only a few thousand years ago, this area was significantly wetter, filled with grasslands, lakes, and rivers. The time referred to as the African humid period extended from approximately 11,000 to 5,000 years ago. The changes in climate were influenced by variations in planet-planet living geosphere's orbit, leading to a shift in sunlight distribution and impacting monsoon patterns. In the humid period, the Sahara hosted a variety of wildlife, such as elephants, giraffes, and hippos. In that place, early humans made their home, creating rock art that illustrated the animals and landscapes familiar to them. As the climate changed and the area became drier, these groups moved, leading to the formation of the desert we recognize today. The transformation of the Sahara serves as a reminder that the climate of our planet is always in flux, influenced by forces that work over millennia. Tropical rainforests generate a significant portion of the oxygen that fills our lungs. Tropical rainforests rank as some of the most productive ecosystems on our planet, brimming with vibrant life and lush vegetation. Plants take in carbon dioxide and give off oxygen during photosynthesis. The incredible abundance of vegetation in tropical rainforests results in the generation of significant quantities of oxygen, although a large portion is utilized by the organisms that inhabit these ecosystems. The Amazon rainforest, frequently referred to as the lungs of the planet-living geosphere, is vital for regulating atmospheric gases and climate. The area also retains significant quantities of carbon within its trees and soil, contributing to the reduction of climate change effects. In addition to producing oxygen, tropical rainforests play a crucial role in maintaining biodiversity, hosting over half of the planet's species, while occupying merely around 6% of the planet-living geosphere's land area. They affect weather patterns, generate clouds, and facilitate water recycling through transpiration. The destruction of tropical rainforests due to deforestation transcends local boundaries, emerging as a worldwide issue that impacts climate, water cycles, and the existence of numerous species. Soil forms over the course of hundreds to thousands of years. Soil may appear ordinary, something we tread upon without much consideration, yet it is a multifaceted and invaluable resource that develops at a remarkably slow pace. Soil originates from rock, which is gradually broken down through the processes of weathering, influenced by water, wind, temperature fluctuations, and the growth of plant roots. The formation of soil can span hundreds to thousands of years, resulting in merely a few centimeters of depth. When organic matter from plants and animals breaks down, it combines with mineral particles, enhancing the soil and enabling it to sustain life. Vibrant soil is alive with a multitude of organisms, including bacteria, fungi, planet-living, geosphere worms, and insects, all collaborating to recycle nutrients. This is the cornerstone of agriculture, the essential element of the food chains that support our existence. Soil is indeed susceptible to erosion and degradation, and when it is lost, it requires centuries for restoration. Each handful of soil tells a story of transformation, serving as a reminder that the planet-living geosphere we stand on is shaped by the passage of deep time. Volcanic vents emit gases that contributed to the formation of planet-living geosphere's gaseous envelope and global ocean system. Volcanic vents are frequently viewed as powerful and destructive entities, capable of unleashing lava flows and ash clouds. However, they have also been instrumental in shaping the environment of our planet. During volcanic eruptions, gases are expelled from the planet-living geosphere's interior, such as water vapor, carbon dioxide, nitrogen, and sulfur compounds. During the early history of planet-living geosphere, volcanic activity was significantly more intense than it is now, leading to the accumulation of these gases in the gaseous envelope. As time passed, water vapor condensed and descended as rain, replenishing the ocean basins. Carbon dioxide contributed to warming the planet via the greenhouse effect, allowing it to be habitable. Even now, volcanic vents play a role in the movement of elements between the planet-living geosphere's interior and its surface. Lava cools and solidifies to form new land, while also enriching soils with essential minerals. Islands formed by volcanic activity, such as Hawaii, emerged solely from eruptions, with layers of basalt accumulating from the ocean's depths. Volcanic vents serve as both creators and destroyers, powerful forces that have influenced our planet since its inception. Geysers and hot springs showcase the warmth that lies beneath the planet-living geosphere's exterior. In various locations globally, water, heated by geothermal energy, erupts through the surface in stunning showcases. Geysers, such as Old Faithful in Yellowstone, regularly erupt jets of boiling water and steam into the gaseous envelope, propelled by the pressure that accumulates beneath the surface. Hot springs are prevalent, bubbling and steaming softly, their waters abundant in dissolved minerals. These features form when water penetrates cracks in the planet-living geosphere, gets heated by the magma or hot rocks beneath, and subsequently rises back to the surface. The water may reach temperatures that can cause burns, and the nearby rocks frequently display bright hues due to minerals such as sulfur and iron. Geysers and hot springs provide a glimpse into the geothermal energy that fuels plate tectonics and powers volcanic vents. These environments serve as homes for extremophile organisms, which are microbes that flourish in conditions lethal to most forms of life. These beings suggest that life could potentially thrive in harsh conditions beyond our planet within the solar system. The frozen water. Approximately 10% of the land surface of planet-living geosphere is covered by ice. When we envision ice, we may conjure images of winter, frost, or ice cubes floating in a beverage. However, our planet contains immense reserves of ice, secured within the polar ice caps and ice rivers. Approximately 10% of the planet-living geosphere's land surface is covered by ice, with the majority located in Antarctica and Greenland. Antarctica contains a vast amount of ice, and if it were to melt completely, it would result in a rise in global sea levels of approximately 60 meters. The thickness of these ice sheets is remarkable, reaching depths of over 4 kilometers in certain areas, and they hold a historical record of planet-living geosphere's climate, spanning hundreds of thousands of years. Ice rivers move gradually downwards, driven by their own mass, sculpting valleys and forming the contours of the land. In mountainous areas, ice rivers supply rivers that deliver water to millions of individuals. The ice at the poles is essential for regulating planet-living geosphere's climate, as it reflects sunlight back into space and contributes to cooling the planet. With increasing temperatures, the ice reserves are diminishing, leading to significant consequences for sea levels and the climate. Ice rivers move gracefully, resembling rivers of ice as they shape the terrain around them. Ice rivers might appear to be immobile, encased in ice, yet they are in a state of continuous movement. As snow builds up, the ice bends and moves gradually down the slope, resembling a river flowing at a leisurely pace. The movement may vary, occurring at just a few centimeters annually or several meters daily, influenced by the ice river's dimensions and the slope of the landscape. Ice rivers move, scraping and grinding the underlying rock, which results in the formation of deep valleys and distinctive features such as fjords and cirques. The rocks and sediment transported by the ice are left behind as moraines once the ice has melted. In the glacial periods, enormous ice rivers blanketed large portions of North America and Europe, transforming the landscapes of the continental plates. Upon their retreat, they abandoned the Great Lakes, numerous smaller lakes, and fertile soils created from glacial till. The landscapes we observe today, across numerous areas, are the result of glacial sculpting, showcasing the incredible ability of ice to mold the planet-living geosphere over millennia. Ice cores provide insights into planet-living geosphere's climate history, extending back hundreds of thousands of years, found deep within the ice sheets of Antarctica and Greenland. Researchers extract cores that offer insights into historical events. As snow descends and solidifies into ice, it encapsulates minuscule air bubbles, safeguarding remnants of the primordial gaseous envelope. Through the examination of these bubbles, researchers are able to assess historical concentrations of carbon dioxide, methane, and various other gases. Isotopes in the ice can also be studied to ascertain historical temperature data. Ice cores provide a comprehensive account of planet, living geosphere's climate history, extending over 800,000 years and illustrating the patterns of glacial periods alongside warmer interglacial phases. The records indicate that the climate of planet living geosphere has fluctuated significantly, influenced by alterations in the planet's orbit and various natural elements. Current levels of greenhouse gases are higher than at any point in the ice core record, clearly demonstrating the impact of human activity on the gaseous envelope. Sea ice drifts upon the ocean's surface, reflecting sunlight back into the vastness of space. In the polar regions, the ocean's surface freezes, resulting in the formation of sea ice. In contrast to icebergs, which are pieces of ice rivers that have detached and drift in the ocean, sea ice is created directly from seawater. When it freezes, salt is released, resulting in fresh ice. Sea ice is essential to planet living geosphere's climate as it reflects sunlight, a characteristic known as albedo. The bright white surface reflects a significant amount of the sun's energy back into space, contributing to the cooling of the polar regions. As sea ice melts, it reveals the darker ocean water underneath, which takes in more heat, resulting in additional warming in a continuous cycle. Sea ice plays a crucial role in polar ecosystems, serving as habitat for species such as seals and polar bears, and underpinning the foundation of the food chain. In recent decades, there has been a notable decline in Arctic sea ice, with reductions observed in both its extent and thickness, a clear indication of a heating world. Icebergs are formed from freshwater ice that has been shaped by ice rivers. Icebergs are large pieces of ice that detach from ice rivers or ice shelves, a phenomenon known as calving. They drift in the sea, with merely around 10% of their bulk exposed above the water, while the remainder remains concealed beneath. This has led to the expression, tip of the iceberg. Icebergs consist of fresh water, created from compacted snow, and they can reach massive sizes. Some are as large as small countries, especially those that detach from the ice shelves of Antarctica. As they move away from the poles, they gradually melt, allowing fresh water to flow into the ocean. This may influence local salinity levels and the movement of ocean currents. Icebergs have historically presented a danger to vessels. The most well-known event is the sinking of the Titanic in 1912. Currently, satellites and patrols keep a close watch on icebergs in shipping lanes. Even with the risks involved, icebergs possess a captivating beauty, shaped by the relentless forces of waves and weather into extraordinary forms, radiating a brilliant blue hue in the sunlight where the ice is densest. Frozen ground layer contains carbon that has remained frozen for millennia. In the Arctic and subarctic areas, a significant portion of the ground remains perpetually frozen. A layer known as frozen ground layer can reach depths of hundreds of meters and has stayed frozen for thousands of years. Buried within this frozen terrain lies a significant quantity of organic material, including deceased plants and animals that have not completely decomposed due to the cold conditions. As long as it remains frozen, this carbon is securely contained. However, with the increase in global temperatures, frozen ground layer is starting to melt. When it does, microbes break down the organic matter, releasing carbon dioxide and methane into the gaseous envelope, both potent greenhouse gases. This creates a feedback loop. Warming leads to thawing, which releases more gases, leading to more warming. The amount of carbon stored in frozen ground layer is roughly twice the amount currently in the gaseous envelope. The fate of this carbon is one of the most significant uncertainties in predicting future climate change. A hidden reservoir that could amplify warming if released. The water cycle. Water cycles endlessly between ocean, air, and land. The water cycle is one of planet-living geosphere's most fundamental processes, a continuous movement of water through the planet's systems. It begins with evaporation, as the sun's heat turns water from global ocean system, lakes, and rivers into vapor. This vapor rises into the gaseous envelope, where it cools and condenses into clouds. Eventually, the water falls back to the surface as precipitation, rain, snow, sleet, or hail. Some of this water flows over the land in rivers and streams, returning to the global ocean system. Some seeps into the ground, replenishing aquifers. Plants absorb water from the soil and release it back into the gaseous envelope through transpiration. This cycle has been repeating for billions of years, distributing water across the planet and making life possible. The water you drink today is the same water that has been cycling through planet-living geosphere's systems since the dawn of time, ancient and endlessly renewed. Rivers carve valleys and transport nutrients to the sea. Rivers are the arteries of the land, carrying water from mountains and highlands down to the global ocean system. As they flow, they shape the landscape, cutting through rock to carve valleys and canyons. Over millions of years, even the hardest stone yields to the persistent flow of water. Rivers transport sediment from fine silt to large boulders, depositing it in floodplains and deltas. These sediments enrich the soil, making river valleys some of the most fertile lands on planet-living geosphere. Rivers also carry nutrients from the land to the sea, feeding coastal ecosystems. Many of the world's great civilizations arose along rivers: the Nile, the Tigris, and Euphrates, the Indus, the Yangtze. Because they provided water, transportation, and fertile soil, even today, rivers are vital for agriculture, drinking water, and energy production. They are dynamic systems, constantly changing their course, flooding, and adapting to the landscape around them. Lakes can be ancient reservoirs of water, millions of years old. Lakes come in many forms, from small ponds to vast inland seas. Some are relatively young, formed by ice rivers during the last ice age. Others are ancient, their waters held in rift, valleys, or volcanic craters for millions of years. Lake Baikal in Siberia is the world's deepest and oldest lake, holding 20% of the world's unfrozen freshwater. It formed in a rift valley more than 25 million years ago and is still deepening. The lake is home to unique species found nowhere else on planet-living geosphere, creatures that have evolved in isolation over millennia. Other ancient lakes include Lake Tanganyika in Africa and Lake Titicaca in the Andes. These lakes are not just bodies of water, but ecosystems unto themselves, with their own climates, currents, and life forms. They are reservoirs of history, their sediments holding clues to past climates and environments. Archives written in layers of mud and organic matter. Waterfalls form, where rivers encounter sudden drops in elevation. Waterfalls are among nature's most awe-inspiring sights, where water plunges over cliffs or steep drops, often creating mist and rainbows. They form where there is a sudden change in elevation along a river's course, typically where hard, resistant rock overlies softer rock. As the river erodes the softer rock, it undercuts the harder layer, creating a vertical drop. Over time, the waterfall may retreat upstream as erosion continues. Some waterfalls are seasonal, flowing only during rainy periods. Others, fed by ice rivers or large rivers, flow year-round with immense force. Angel Falls in Venezuela is the tallest waterfall in the world, plunging more than 900 meters. Victoria Falls on the Zambezi River is one of the largest by volume, creating a curtain of water over a kilometer wide. Waterfalls are dynamic features, constantly reshaping the landscape, and they play a role in aerating water and supporting aquatic ecosystems. Wetlands filter water, and provide habitat for countless species. Wetlands, including swamps, marshes, and bogs, are areas where water covers the soil for at least part of the year. They might seem like marginal, muddy places, but they are among the most productive ecosystems on planet-living geosphere. Wetlands act as natural filters, trapping sediments and absorbing pollutants before they reach rivers and global ocean system. They also store carbon in their waterlogged soils, making them important in the fight against climate change. Wetlands are biodiversity hotspots, providing habitat for a wide range of species, from waterfowl and amphibians to fish and invertebrates. Many migratory birds depend on wetlands as resting and feeding grounds along their journeys. Despite their importance, wetlands have been drained and filled for agriculture and development, and more than half of the world's wetlands have been lost. Protecting and restoring wetlands is crucial for maintaining healthy water systems and supporting the species that depend on them. Groundwater, hidden beneath the surface, supplies much of our drinking water. Beneath the land surface, water fills the spaces between rocks and soil particles, creating vast underground reservoirs called aquifers. This groundwater is a critical source of drinking water for billions of people and is used extensively for irrigation. It moves slowly, seeping through the ground over weeks, years, or even centuries, depending on the geology. Some aquifers are recharged relatively quickly by rainfall and rivers. Others, called fossil aquifers, contain water that accumulated thousands of years ago and are not replenished at significant rates. Pumping water from these aquifers faster than they can recharge leads to depletion, causing wells to run dry and land to subside. Groundwater also feeds springs and streams, maintaining flow even during dry periods. It is a hidden but vital part of the water cycle, a resource we rely on but often take for granted. Managing groundwater sustainably is essential for ensuring future water security. Springs bring groundwater to the surface in natural fountains. In some places, groundwater emerges naturally at the surface, forming springs. These can range from small seeps to large flows that create rivers. Springs occur where the water table intersects the land surface or where geological features channel water upward. The water from springs is often cool and clear, filtered through layers of rock. Some springs are thermal, heated by geothermal energy, and can be hot enough to scald. Springs have long been important to human settlements, providing reliable sources of fresh water in arid regions. Many towns and cities were founded near springs. In addition to their practical uses, springs are often places of natural beauty, with lush vegetation and unique ecosystems supported by the constant flow of water. They remind us of the hidden waters beneath our feet, brought to light by the geology of the land. The largest river basin discharges more water into the ocean than any other river. The largest river basin, flowing through the heart of South America, is the largest river in the world by volume. It carries an astonishing amount of water, discharging approximately 200,000 cubic meters per second into the Atlantic Ocean, more than the next 7 largest rivers combined. The Amazon drains a basin covering more than 7 million square kilometers, an area nearly as large as the continental United States. Its water comes from countless tributaries, fed by rain that falls in the Amazon rainforest. The river is so vast that in some places you cannot see from one bank to the other, and its mouth is over 300 kilometers wide. The discharge of the Amazon influences ocean salinity and currents far from the coast. During the wet season, the river floods vast areas of forest, creating a dynamic environment where fish and other aquatic life thrive. The Amazon is not just a river but a lifeline, supporting the rainforest and the millions of people who depend on it. The weather. Weather is driven by the uneven heating of planet-living geosphere's surface. Every gust of wind, every cloud, every rainstorm can be traced back to one fundamental cause. The sun heats planet-living geosphere's surface unevenly. The equator receives more direct sunlight than the poles, creating temperature differences. Warm air rises, creating areas of low pressure, while cool air sinks, creating high pressure. Air flows from high to low pressure, creating wind. The sun also evaporates water from the global ocean system, adding moisture to the air. As this moist air rises and cools, water vapor condenses into clouds and eventually falls as precipitation. Planet living. Geosphere's rotation further complicates these patterns, deflecting winds and creating the swirling motion of storms. Mountains, global ocean system, and ice also influence weather by altering temperature and moisture. The result is a constantly changing tapestry of weather, from calm, sunny days to violent tropical cyclones, all driven by the simple fact that the sun shines more strongly in some places than others. Tropical cyclones are among planet-living geosphere's most powerful storms. Tropical cyclones, also called typhoons or cyclones depending on where they occur, are massive rotating storms that form over warm tropical global ocean system. They begin as clusters of thunderstorms that organize around a center of low pressure. As warm, moist air rises and releases its heat, it fuels the storm, causing winds to spiral faster and faster. The storm can grow hundreds of kilometers wide, with winds exceeding 250 kilometers per hour. At the center is the eye, a region of calm where air sinks and skies are often clear. Surrounding the eye is the eye wall, where the strongest winds and heaviest rains occur. Tropical cyclones derive their energy from warm ocean water, typically needing sea surface temperatures above 26 degrees Celsius. As they move over land or cooler water, they lose their fuel and weaken. Despite their destructive power, tropical cyclones play a role in distributing heat from the tropics toward the poles, helping to balance planet-living geosphere's energy budget. Tornadoes are violent columns of rotating air. Tornadoes are among the most intense and localized weather phenomena on planet-living geosphere. They form as rotating columns of air, extending from a thunderstorm to the ground, often visible as a funnel cloud, surrounded by debris. The winds in a tornado can exceed 300 kilometers per hour, powerful enough to level buildings and toss vehicles like toys. Tornadoes form when conditions are just right, typically when warm, moist air meets cool, dry air in an unstable gaseous envelope. Wind shear, a change in wind speed or direction with height, can cause the air to rotate. If this rotation tightens and extends downward, a tornado is born. Most tornadoes are relatively weak and short-lived, but a few become violent monsters that carve paths of destruction tens of kilometers long. The United States sees more tornadoes than any other country, particularly in an area known as Tornado Alley. Despite advances in forecasting, tornadoes remain difficult to predict, forming quickly and sometimes with little warning. Monsoons bring life-giving rains to billions of people. Monsoons are seasonal wind patterns that bring dramatic changes in weather, most notably heavy rains. They occur in tropical and subtropical regions, driven by the differential heating of land and sea. During summer, the land heats up faster than the ocean, creating low pressure over the continent. Moist air from the ocean flows inland to fill this low, bringing heavy rains. In winter, the pattern reverses, and dry air flows from the land to the sea. The most well-known monsoon occurs in South Asia, where the summer monsoon brings the majority of the year's rainfall to India, Bangladesh, and surrounding countries. This rain is crucial for agriculture, replenishing rivers and groundwater. Billions of people depend on the monsoon for their livelihoods. However, the monsoon can also bring flooding and landslides. Its timing and intensity vary from year to year, influenced by ocean temperatures and other factors, making it a central concern for the region's climate and economy. Droughts can last for years, reshaping landscapes and societies. A drought is an extended period of abnormally low rainfall, leading to water shortages. While a few weeks without rain might be inconvenient, true droughts last months or years, with profound consequences. Soils dry out, rivers and lakes shrink or disappear, and vegetation dies. Agriculture suffers, leading to food shortages and economic hardship. In severe cases, droughts trigger famines, and mass migrations, droughts have shaped human history, contributing to the collapse of civilizations. The ancient Maya, the Akkadian Empire, and the ancestral Puebloans all faced prolonged droughts that stressed their societies. Droughts are a natural part of planet-planet living, geosphere's climate variability, often linked to ocean temperature patterns like El Niño and La Niña. However, climate change is altering drought patterns, making some regions drier and increasing the frequency and severity of droughts. Understanding and preparing for droughts is essential for water management and food security in a changing world. Snow forms from ice crystals that grow in cold clouds. Snowflakes are one of winter's simple beauties, but their formation is a marvel of physics. Snow forms when water vapor in a cloud freezes directly into ice crystals, bypassing the liquid phase, a process called deposition. The crystals grow as more vapor freezes onto them, forming intricate six-sided shapes. The exact shape depends on temperature and humidity as the crystal falls through the cloud. No two snowflakes are alike, though they share the hexagonal symmetry imposed by the molecular structure of ice. Some are simple plates or columns, while others develop elaborate branching patterns. When many snowflakes clump together, they form the soft flakes we see falling. On the ground, snow provides insulation, protecting plants and animals from extreme cold. It also stores water, slowly releasing it as it melts in spring, feeding rivers and recharging aquifers. In regions that depend on snowmelt for water, the snowpack is carefully monitored as a critical resource. Hail forms in strong thunderstorms with powerful updrafts. Hailstones are lumps of ice that fall during thunderstorms, sometimes growing large enough to cause significant damage. They form in towering cumulonimbus clouds with strong updrafts. A hailstone begins as a small ice pellet or frozen raindrop. As it falls, the updraft carries it back up into the cold part of the cloud, where more water freezes onto it. This process can repeat multiple times, adding layer upon layer of ice. If you cut a hailstone in half, you can often see these layers, like rings in a tree. Ultimately, the hailstone grows too heavy for the updraft to sustain, leading it to descend to the ground. The majority of hail is small, typically around the size of peas, or even smaller, and it tends to melt rapidly upon impact with the ground. In intense storms, hail can reach the size of golf balls, or even larger, striking with sufficient force to shatter windows, dent vehicles, and harm crops. The biggest hailstone ever documented in the United States measured almost 20 centimeters across. Fog is essentially a cloud that forms right at the surface of the planet-living geosphere. On a cool, humid morning, you may awaken to discover the world enveloped in fog, a dense mist that restricts visibility to only a few meters. Fog is essentially similar to a cloud. A cloud that has developed at or close to the ground is what it is. It happens when the air close to the ground cools down to its dew point, which is the temperature at which water vapor turns into small droplets. Various kinds of fog exist. Radiation fog develops during clear, tranquil nights, as the ground quickly loses heat, leading to a drop in temperature of the air above. Advection fog forms when warm, moist air travels over a cooler surface, such as when sea air flows over cold coastal waters. Valley fog develops as cold air settles into lower regions. Fog possesses a haunting beauty, gently softening the landscape and dampening sounds. It presents dangers for travel, diminishing visibility on roads and waterways. It contributes to ecosystems by supplying moisture to plants in regions with limited rainfall. The wind cannot be seen, but it molds the environment around us. Wind is essentially air in movement, traveling from regions of high pressure to those of low pressure. Even though it remains invisible, its presence is evident in the gentle rustling of leaves, the graceful flight of birds, and the crisp chill that accompanies a cold day. Wind plays a crucial role in redistributing heat and moisture across the globe, influencing climates and steering weather patterns. It drives ocean currents and generates waves. Over extended durations, wind wears away rocks, and carries sediment, shaping the terrain into dunes, ventifacts, and various other formations. For thousands of years, humans have utilized the wind, using it to fill sails and power windmills. Currently, wind turbines produce electricity by harnessing this natural energy flow. The patterns of the wind are intricate, shaped by the planet, living geosphere's rotation, atmospheric heating, and the landscape's topography. At its essence, wind arises from the sun's uneven heating, serving as a reminder that the invisible forces surrounding us are integral to planet living geosphere's interconnected systems. Rainbows form when sunlight bends as it passes through water droplets. Rainbows are temporary bands of color that emerge in the sky, typically following a rainstorm. Sunlight enters water droplets in the air, leading to their formation. When light transitions from air into water, it experiences a reduction in speed and changes direction, a phenomenon known as refraction. Various colors of light refract to different extents, with violet experiencing the greatest bending and red the least. Within the droplet, light reflects from the rear surface and then refracts once more as it leaves. This divides the white sunlight into its individual colors, resulting in a spectrum ranging from red to violet. To see a rainbow, the sun needs to be positioned behind you, while rain or mist should be present in front of you. Occasionally, a double rainbow can be observed, featuring a second, more delicate arc positioned above the first, showcasing the colors in reverse order. Rainbows have sparked myths and tales throughout various cultures, frequently regarded as emblems of hope or connections between realms. They serve as reminders of the beauty that arises when light and water converge, showcasing life on planet-living geosphere. Life on planet-living geosphere originated in the global ocean system over 3.5 billion years ago. The narrative of life on our planet is one of remarkable adaptation and unwavering resilience. More than 3.5 billion years ago, the first living organisms emerged in the global ocean system, likely around hydrothermal vents or in shallow tidal pools. In the beginning, life consisted of basic, single-celled microbes, yet they had the remarkable capability to reproduce and evolve. Throughout billions of years, life has evolved, creating various methods to harness energy and engage with the surroundings. Photosynthetic bacteria adapted to utilize sunlight, producing oxygen as a byproduct. The gradual accumulation of oxygen in the gaseous envelope altered planet-living geosphere's chemistry, setting the stage for the emergence of more complex life forms. Ultimately, multicellular organisms emerged, resulting in the remarkable diversity reflected in the fossil record. Life has endured several mass extinctions, consistently recovering and occupying ecological niches. Currently, life flourishes in almost every habitat on our planet, ranging from the depths of the ocean to the heights of the gaseous envelope, showcasing its remarkable ability to adapt. Photosynthesis changed the composition of planet-living geosphere's gaseous envelope through the generation of oxygen. During a significant portion of planet-living geosphere's early history, the gaseous envelope had minimal to no free oxygen present. Approximately 2.5 billion years ago, cyanobacteria, which are photosynthetic microbes, started to generate oxygen as a byproduct of the process of photosynthesis. Initially, this oxygen was taken up by dissolved iron in the global ocean system, resulting in the formation of iron oxide that accumulated on the ocean floor, leading to the creation of banded iron formations. Ultimately, the global ocean system reached a point of saturation, leading to the accumulation of oxygen in the gaseous envelope. The Great Oxidation Event was disastrous for numerous anaerobic organisms that were unable to withstand oxygen. However, it paved the way for aerobic life, organisms that utilize oxygen to metabolize food with greater efficiency. The increase in oxygen levels facilitated the development of intricate, multicellular organisms. Life on planet-living geosphere would be drastically altered without photosynthesis and the oxygen it generates. Currently, plants, algae, and cyanobacteria are still generating the oxygen we rely on, supporting the extensive network of life. The variety of life on our planet is astonishing and largely unexplored. It is estimated by scientists that approximately 8.7 million species of plants, animals, and microbes exist on planet-living geosphere. Yet only around 1.2 million have been formally documented. The others stay concealed, tucked away in tropical rainforests, the depths of global ocean system, and beneath the soil. Each year, countless new species are identified, ranging from minuscule insects to sizable mammals. The distribution of this diversity is not uniform. Tropical regions, particularly tropical rainforests and coral reefs, serve as biodiversity hotspots, hosting the majority of species. Every species has a specific function within its ecosystem, aiding in essential processes such as pollination, decomposition, and the cycling of nutrients. Biodiversity offers resilience, enabling ecosystems to endure disturbances. It also offers resources for people, ranging from food and medicine to ecosystem services, such as clean air and water. Biodiversity faces significant threats due to habitat loss, pollution, climate change, and overexploitation. Safeguarding the variety of life extends beyond merely maintaining species. It focuses on preserving the operations of the systems that sustain all forms of life, including humanity. Fungi link the forest, creating extensive subterranean systems. Underneath the forest floor exists a concealed realm of fungi, with their thread-like formations known as hyphae, intricately interlacing through the soil. These fungi establish symbiotic connections with plant roots, resulting in the formation of structures known as mycorrhizae. The fungi enhance the plant's root system, facilitating the absorption of essential water and nutrients, such as phosphorus and nitrogen. The fungi receive sugars produced by the plant through photosynthesis in exchange. However, the network extends beyond just individual plants. The mycorrhizal fungi link various trees and plants, enabling them to exchange resources. A substantial tree that receives ample sunlight could transfer sugars to a smaller, shaded seedling via this network. Trees have the ability to send warning signals via fungi when they are under attack by insects, which encourages nearby trees to bolster their defenses. This interconnected network of trees challenges the notion of them as solitary beings, showcasing their role within a collaborative ecosystem. The largest living organism on planet-living geosphere is thought to be a honey fungus, located in Oregon, with its underground network covering thousands of acres. Microbes are more numerous than any other type of life on planet-living geosphere. When considering life, we frequently envision animals and plants. The overwhelming majority of life on planet-living geosphere exists at a microscopic level. Microbes, such as bacteria, archaea, and protists, inhabit a wide range of environments, including the soil underfoot, the air around us, the depths of the global ocean system, and even within our own bodies. A single gram of soil may harbor billions of bacteria, while the human body is home to trillions of microbial cells, surpassing the number of our own cells. These microbes are essential in ecosystems, as they decompose organic matter, cycle nutrients, fix nitrogen, and even produce oxygen. Certain organisms thrive in extreme conditions, ranging from scalding hot springs to icy Antarctic lakes, environments where no other forms of life can endure. These extremophiles broaden our comprehension of the potential habitats for life, suggesting intriguing possibilities on other planets. Even though they are crucial, the majority of microbes remain uncultured and unexamined, highlighting a significant area for biological exploration. Trees have the remarkable ability to endure for millennia, standing as quiet observers of the unfolding of history. Certain trees possess lifespans that far exceed those of humans, enduring for millennia. The bristlecone pines, found in the mountains of California and Nevada, are recognized as the oldest known trees. One, referred to as Methuselah, boasts an age exceeding 4,800 years, rendering it older than the pyramids of Egypt. These trees develop at a gradual pace, enduring tough circumstances, which plays a significant role in their long lifespan. Their wood boasts a high density, making it resistant to both rot and insect damage. Every year, they form a new ring of growth, documenting the environmental conditions experienced. Scientists can reconstruct past climates, droughts, and even volcanic eruptions by studying tree rings. These timeless trees have endured the ebb and flow of civilizations, through conflicts and harmony, through shifts in climate and terrain. They serve as connections to history, quiet observers of thousands of years, reminding us of the vast timelines of nature, evolution, and extinction. Life progresses through the process of natural selection over numerous generations. Evolution refers to the gradual changes in living organisms over time, influenced by the mechanism of natural selection. Members of a species exhibit variations in their characteristics, with certain traits being passed down through inheritance. In situations where resources are scarce, those who possess characteristics that enhance their survival and reproductive success are more inclined to transmit those characteristics to their offspring. Through numerous generations, these beneficial characteristics become increasingly prevalent, leading to the evolution of the population. This process continues to unfold, influencing the variety of life we observe in the present day. The concept of evolution clarifies how organisms adapt perfectly to their surroundings, illustrated by the sleek form of a fish and the disguising patterns of a moth. This also illustrates the connections among species, demonstrating that all life on planet-living geosphere is derived from common ancestors. Evolution does not follow a straightforward path toward complexity. Rather, it resembles a branching tree, with numerous lineages splitting and diverging over the course of billions of years. This principle serves as a fundamental connection in biology, linking all living organisms through a common history. Life on planet-living geosphere, has been reshaped multiple times by mass extinctions. Throughout the history of our planet, there have been times when a considerable proportion of all species disappeared in a brief span. Mass extinctions, frequently caused by catastrophic events, significantly altered the trajectory of evolution. The most well-known event is the extinction at the conclusion of the Cretaceous period, 66 million years ago, when an asteroid impact and volcanic eruptions resulted in the extinction of the Mesozoic reptiles. Additionally, there have been other significant events, such as the Permian-Triassic extinction, recognized as the most severe in planet-living geosphere's history, resulting in the loss of over 90% of species. After mass extinctions, there are phases of recovery and diversification, during which the surviving species adapt and evolve to occupy the vacant ecological niches. The extinction of the Mesozoic reptiles enabled mammals to diversify, ultimately leading to the emergence of humans. Currently, a number of scientists contend that we are experiencing a sixth mass extinction, largely caused by human actions, with species vanishing at rates significantly higher than the normal background extinction rate. For more than 160 million years, Mesozoic reptiles were the dominant creatures on planet-living geosphere. Mesozoic reptiles emerged approximately 230 million years ago and dominated the planet-living geosphere for over 160 million years. Their diversity was remarkable, encompassing the enormous, long-necked sauropods and the formidable carnivorous theropods, such as Tyrannosaurus rex, alongside the armored ankylosaurs and the agile velociraptors. Some Mesozoic reptiles were as small as chickens, whereas others, such as Argentinosaurus, could weigh as much as multiple elephants. Although often viewed as cold-blooded reptiles, there is evidence indicating that many Mesozoic reptiles were actually active, warm-blooded beings, with some even possessing feathers. Mesozoic reptiles inhabited all continental plates and adjusted to various environments. Their dominance concluded suddenly 66 million years ago when an asteroid impacted the Yucatan Peninsula, initiating climate shifts that the majority could not endure. However, their legacy continues through birds, which are direct descendants of theropod Mesozoic reptiles. Each bird you encounter is, In a way, a living dinosaur. The asteroid impact that brought the age of Mesozoic reptiles to a close created a colossal crater. The proof of the asteroid collision that led to the extinction of the Mesozoic reptiles is found in a large crater hidden under the Yucatan Peninsula in Mexico, referred to as the Chicxulub crater. Measuring over 180 kilometers in diameter, it stands as one of the largest impact structures on our planet. The asteroid, responsible for its creation, measured approximately 10 kilometers in width and was moving at speeds of several tens of kilometers per second. The energy released from the impact was equivalent to billions of nuclear bombs, vaporizing rock and propelling debris high into the gaseous envelope. The debris obstructed sunlight, leading to a significant drop in global temperatures and stopping photosynthesis in its tracks. Wildfires swept through various continental plates. Acid rain descended. The ensuing climate change persisted for years, possibly decades, wreaking havoc on ecosystems. Big creatures, such as the Mesozoic reptiles, were unable to endure. The crater was uncovered in the late 20th century, concealed under layers of sediment. However, its impacts transformed life on planet living geosphere, delineating the division between the era of reptiles and the era of mammals. Fossils provide a glimpse into the life of the past. Fossils represent the preserved remains or traces of ancient organisms. These occur when an organism is rapidly buried post-mortem, safeguarding it from decomposition. As time passes, minerals infiltrate the bones or shells, substituting organic material and transforming them into stone. At times, whole organisms find preservation in amber, ice, or tar. Fossils serve as direct evidence of life from the past, revealing the appearance of organisms, their lifestyles, and the changes they underwent through time. They uncover beings that have vanished from our world, such as trilobites, ammonites, and woolly mammoths. Fossils assist scientists in piecing together ancient environments and monitoring mass extinctions. The fossil record is not fully comprehensive, since fossilization depends on particular conditions being met. However, what has been retained provides essential understanding. Every fossil serves as a snapshot, capturing a moment in time and linking us to the profound history of life on our planet. Coal and oil originate from the remnants of ancient organisms. The energy sources we depend on, including coal, oil, and natural gas, are the altered remnants of organisms that existed millions of years in the past. Coal originated from vegetation that thrived in marshy woodlands during the Carboniferous period, approximately 300 million years ago. Upon their demise, these plants were interred beneath layers of sediment prior to complete decomposition. With the passage of time, they underwent a transformation due to heat and pressure, resulting in coal. Oil and natural gas originated from tiny marine organisms, such as plankton and algae, that gathered on the ocean floors over time. The organic material, buried beneath layers of sediment, was subjected to planet-living geosphere's heat, leading to its transformation into hydrocarbons. These fuels retain energy from sunlight that was captured through photosynthesis in ancient times. Releasing that energy through extraction and burning also emits carbon dioxide that was previously stored, which contributes to climate change. By utilizing fossil fuels, we are, in a way, drawing from the distant past, engaging with the remnants of ecosystems that thrived long before humanity emerged on the planet. Humans represent a relatively new chapter in the story of planet-living geosphere. Imagine condensing the entire 4.6 billion years of planet-living geosphere's history into just one day. Humans would emerge in the final moments, just before midnight. Homo sapiens, our anatomically modern species, have been around for roughly 300,000 years, which is merely a fleeting moment in the grand timeline of geology. During the majority of that period, we existed as hunter-gatherers within small communities. Agriculture started approximately 10,000 years ago, leading to the emergence of civilizations soon after. The phenomenon of industrialization, which has significantly influenced the planet-living geosphere, has a history spanning fewer than 300 years. In this remarkably brief period, humans have expanded their presence worldwide, transformed landscapes, tamed animals and plants, and created technology that enables us to change the environment on a global level. As a relatively new species, our impact is remarkably significant. Grasping our position in the vast timeline of planet, living geosphere can foster a feeling of humility and accountability, serving as a reminder that we are integral to a much grander narrative. Geology and time. Rocks are categorized into three distinct types, depending on their formation process. Rocks, the solid substances that constitute planet living geosphere's crust, are classified into three primary categories: igneous, sedimentary, and metamorphic. Igneous rocks are created when molten magma, or lava, cools and solidifies. When magma cools gradually below the surface, it results in the formation of coarse-grained rocks, such as granite. When lava cools rapidly at the surface, it results in the formation of fine-grained rocks, such as basalt. Sedimentary rocks originate from the accumulation of particles derived from other rocks, minerals, or organic materials. These particles gather in layers and undergo compaction and cementation over time. Examples include sandstone, limestone, and shale. These rocks frequently hold fossils and offer insights into previous environments. Metamorphic rocks develop when pre-existing rocks experience heat, pressure, or chemical processes deep within the planet living geosphere, resulting in their transformation into new varieties. Marble, which originates from limestone, and slate, which comes from shale, are classified as metamorphic rocks. The rock cycle links these types, as rocks can be broken down, reformed, and transformed over millions of years, continuously recycling planet living geosphere's materials. The oldest rocks on our planet date back more than 4 billion years. The oldest rocks on planet living geosphere offer a window into the early days of our planet. The acastagonite in Canada ranks as one of the oldest known rocks, with an age of approximately 4 billion years. Zircon crystals, discovered in Western Australia, date back approximately 4.4 billion years, establishing them as the oldest known materials, originating from planet living geosphere. These ancient rocks and minerals have withstood billions of years of geological processes, such as erosion, volcanism, and plate tectonics. They inform us about the conditions on early planet living geosphere, indicating that liquid water, and perhaps even continental plates, were present much earlier than previously believed. Examining these ancient materials aids scientists in comprehending the formation of planet living geosphere's crust and the planet's evolution from a molten state into a world characterized by global ocean system and file. Continental plates. The majority of rocks are relatively young, continually undergoing recycling within the rock cycle. These ancient survivors serve as invaluable records of our deep past. The movement of plate tectonics is fueled by the heat that escapes from the interior of the planet living geosphere. The motion of planet living geosphere's tectonic plates is driven by heat originating from the planet's interior. The heat originates from two primary sources: the residual heat left over from the formation of the planet living geosphere and the radioactive decay of elements such as uranium and thorium found in the mantle layer and crust. The heat generates convection currents within the mantle layer as hot material ascends, cools down, and then descends, resulting in a gradual circulation pattern. The currents pull the tectonic plates above, leading to their movement. In regions where tectonic plates meet, one plate can be pushed down beneath another, creating a subduction zone that facilitates the recycling of crustal material into the mantle layer. At locations where tectonic plates separate, fresh crust emerges from rising magma, resulting in the formation of mid-ocean ridges. This process has persisted for billions of years, continuously transforming the surface. Plate tectonics is distinctive to planet living geosphere compared to other planets in our solar system. and it is essential for regulating climate, recycling carbon, and forming varied environments that sustain life. Seismic events unleash energy accumulated along fault lines. Planet-planet living geosphere quakes occur as a sudden shaking of the ground, resulting from the release of energy within planet-planet living geosphere's crust. Most take place along faults and fractures, where blocks of rock slide past one another. Tectonic plates are always moving, yet friction at faults can cause them to become stuck. Stress accumulates over the course of years, decades, or even centuries. Ultimately, the pressure surpasses the resistance, causing the rocks to shift and unleash energy in the form of seismic waves. The waves spread outwards, trembling the planet-living geosphere beneath. The location where the rupture initiates is referred to as the focus or hypocenter, while the point directly above it on the surface is known as the epicenter. Planet living geosphere quakes differ significantly in strength. Minor incidents happen frequently and often go unnoticed, whereas major events can lead to significant destruction. The most powerful planet-living geosphere quakes, such as the magnitude 9 quake that hit Japan in 2011, have the ability to slightly alter the planet-living geosphere's axis and reduce the length of the day by mere microseconds, highlighting the tremendous forces operating beneath us. Volcanic eruptions have the potential to cool the planet by obstructing sunlight. Although volcanic vents are frequently linked to heat and devastation, significant eruptions can, in fact, lead to a temporary cooling of the planet. A volcanic eruption can release significant quantities of ash and sulfur dioxide into the stratosphere in an explosive manner. The reaction of sulfur dioxide with water vapor leads to the formation of sulfate aerosols, which are minuscule particles that reflect sunlight away from the planet-living geosphere. This may decrease the quantity of solar energy that reaches the surface of the planet-living geosphere, resulting in lower temperatures. The eruption of Mount Pinatubo in the Philippines in 1991 stands out as one of the most significant volcanic events of the 20th century. It reduced global temperatures by approximately ½ degree Celsius for a few years. Historical eruptions, such as Tambora in 1815, resulted in significant consequences, culminating in the year without a summer in 1816, which brought about crop failures and famines. Volcanic eruptions serve as a reminder of the interconnectedness of planet-living geospheres systems, illustrating how occurrences in one region can impact the entire globe. Mountains form and erode over the span of millions of years. Mountains might appear timeless, yet they are in a state of constant transformation. Tectonic forces are responsible for their creation, arising from the collision of plates, volcanic activity, or the uplifting of crustal blocks along faults. As soon as they are formed, erosion starts to wear them down right away. Water, manifesting as rain, rivers, and ice rivers, stands as one of the most formidable agents of erosion. It shapes valleys, moves sediment, and gradually diminishes peaks. Wind, variations in temperature, and the presence of plant roots all play a role in the disintegration of rock. Over the course of millions of years, even the highest peaks can be worn down to mere hills. The Appalachian Mountains, located in the eastern United States, were once comparable in height to the collisional mountain range. However, they were formed hundreds of millions of years ago and have undergone significant erosion since then. The sediments that are worn away from mountains are transported by rivers to the ocean, where they gather and may eventually be raised to create new mountains, perpetuating the cycle. Mountains stand as symbols of tectonic strength and as enduring reminders of the unyielding power of erosion. Rivers shape canyons over the course of millions of years. Canyons are profound, slender valleys characterized by steep walls, typically shaped by rivers eroding rock over vast stretches of time. The Grand Canyon in Arizona stands out as a prominent illustration, where the Colorado River has carved through rock layers over millions of years, resulting in a gorge exceeding a mile in depth, and showcasing nearly 2 billion years of planet-living geospheres. geological history within its walls. The river wears away the rock due to the power of flowing water, particularly during floods, as it transports abrasive sediment. As time progresses, the river carves deeper into the planet-living geosphere, while the surrounding walls undergo weathering and erosion, leading to a broader canyon. The rock layers visible in canyon walls narrate tales of long-ago environments, ranging from shallow seas to arid deserts, with each layer representing a chapter in the history of our planet. Canyons are ever-evolving terrains, continuously transforming even now, although these alterations happen at such a gradual pace that we cannot notice them without precise observation. These structures stand as testaments to the might of water and the flow of time, reflecting the changes of seasons and climate. The tilt of the planet-living geosphere is responsible for the variation in seasons. The seasons spring, summer, fall, and winter are determined not by how far the planet-living geosphere is from the sun, but rather by the tilt of its axis. The tilt of planet-living geosphere's axis is approximately 23.5 degrees in relation to its orbit around the Sunday. As the planet-living geosphere moves along its orbit, various regions of the planet experience varying amounts of direct sunlight. During the time when the northern hemisphere is angled toward the sun, it undergoes summer, characterized by extended daylight hours and heightened sunlight intensity. Concurrently, the southern hemisphere is angled away, undergoing winter. After 6 months, the circumstances change completely. At the equator, the seasons are not very distinct, as the variation in sunlight received remains minimal all year round. If planet-living geosphere lacked this axial tilt, it would experience no seasons, resulting in a more uniform climate that would be considerably less dynamic. The tilt probably resulted from the same colossal impact that created Earth's satellite, a tumultuous occurrence that influenced not only planet-living geosphere's companion, but also the cadence of life on the planet's surface. The equinoxes signify the times when day and night share equal duration. Twice a year, approximately on March 20 and September 22, planet-living geosphere attains a position in its orbit where the axis is aligned neither toward nor away from the Sunday. During the equinoxes, the sun rises directly in the east and sets directly in the west, resulting in nearly equal lengths of day and night across the globe. The term equinox is derived from Latin, signifying equal night. These moments signify the shifts between seasons. The spring equinox signals the onset of spring in the northern hemisphere, while ushering in fall in the southern hemisphere, with the autumn equinox representing the reverse transition. Throughout history, various ancient cultures acknowledged the equinoxes as important moments, constructing monuments that were precisely aligned with the sunrise or sunset during these periods. Examples include Stonehenge in England and the Temple of Kukulkan in Mexico. The equinoxes serve as a reminder of the consistent and reliable patterns of planet-living geosphere's movement, cycles that have shaped life for billions of years. The solstices mark the extremes of daylight, representing the longest and shortest days of the year. The solstices take place when the tilt of the planet-living geosphere is at its most significant angle in relation to the Sunday. The summer solstice occurs around June 21 and marks the longest day of the year in the northern hemisphere, as the North Pole is tilted most directly toward the Sunday. On this day, the sun attains its peak position in the sky, and the duration of daylight is at its maximum. In the southern hemisphere, it marks the winter solstice, the day with the least amount of daylight. Half a year later, approximately on December 21, the circumstances change direction. The winter solstice signifies the briefest day in the northern hemisphere and the most extended day in the southern hemisphere. Following the winter solstice, the days slowly become longer, paving the way for spring. Throughout history, various cultures have honored the solstices, commemorating them with festivals and rituals. The arrival of extended daylight following the winter solstice represented a sign of renewal and optimism. a commitment that the frigid, shadowy days would eventually yield to brightness and comfort again. Tropical regions experience the highest intensity of direct sunlight throughout the entire year. At the equator, the sun's rays hit the planet-living geosphere nearly straight on all year round, providing strong and steady sunlight. Tropical regions are warm due to their consistent exposure to sunlight, which results in a lack of the distinct seasons found in higher latitudes. Many tropical regions experience wet and dry seasons, influenced by changes in wind patterns and ocean currents. The bright sunlight and warmth foster vibrant tropical rainforests, which flourish due to the plentiful energy and moisture available. The warmth of tropical global ocean system contributes to the development of weather systems such as tropical cyclones. The steady presence of sunlight in the tropics has influenced the development of life, resulting in some of the most diverse ecosystems on our planet. The tropics serve as a vibrant hub of energy and productivity, encircling the planet's equator, where life thrives in an astonishing array of forms. However, this very consistency renders tropical ecosystems susceptible to alterations, as the organisms within may be less equipped to handle temperature variations. The polar regions undergo extended periods of either continuous daylight or complete darkness. The poles experience unique conditions due to the extremes of planet-living geosphere's tilt. In the summer, the sun remains visible, moving around the sky for extended periods, a phenomenon known as the midnight Sunday. During winter, the reverse takes place. During polar night, the sun does not rise, and darkness dominates for an extended duration. The polar extremes significantly influence life in remarkable ways. Animals and plants have adjusted to the extended summer days, thriving and reproducing quickly. While during the severe, dark winters, many enter a state of dormancy or migrate. Indigenous peoples residing in the Arctic have cultivated cultures that are in harmony with these cycles, honoring the sun's return following the extended winter. The polar regions present a challenging environment, yet they are also realms of striking beauty, where the interplay of light and shadow unfolds across the sky and ice. Climate zones are defined by factors such as latitude, altitude, and closeness to bodies of water. The climate of our planet exhibits a remarkable range, encompassing everything from blistering deserts to icy polar regions, and from humid tropical rainforests to mild grasslands. Various factors shape these climate zones. Latitude plays a vital role, as it dictates the amount of sunlight that a particular area gets. The equatorial regions experience warmth, in contrast to the cold temperatures found in polar regions. Elevation is significant as well. Mountains can experience snow even close to the equator due to the cooler temperatures found at higher elevations. The closeness to significant water bodies influences temperature regulation, given that water has a slower rate of heating and cooling compared to land. Coastal regions generally experience milder climates compared to inland areas situated at the same latitude. Climate is further influenced by wind patterns, ocean currents, and local topography. The interplay of these factors results in the diverse and intricate array of climates found on planet-living geosphere. Grasping the concept of climate zones allows us to recognize the variety of environments present on planet-living geosphere, as well as the adaptations that organisms have developed to flourish within them. Ocean currents have a significant impact on climate, even in areas that are distant from the shoreline. The global ocean system are ever-changing. They are always moving, with currents streaming like rivers across the ocean. These currents carry significant quantities of heat, affecting the climate in areas distant from the source of that heat. Warm currents, such as the Gulf Stream, transport heat from tropical regions to the poles, thereby enhancing the climates of areas like northwestern Europe. If it weren't for the Gulf Stream, cities such as London and Paris would experience significantly colder temperatures, resembling the climate found in Canada at comparable latitudes. Cold currents, such as the California current, transport cool water from higher latitudes towards the equator, helping to moderate coastal temperatures. Ocean currents play a significant role in shaping precipitation patterns, by impacting the moisture levels in air masses. Alterations in ocean currents, particularly those linked to El Niño occurrences, can lead to significant impacts on global weather patterns, highlighting the interrelated nature of the planet-living geosphere's climate system. El Niño and La Niña represent natural climate patterns that influence weather across the globe. Every few years, the tropical Pacific Ocean experiences a change in temperature patterns, referred to as El Niño or La Niña. In the event of El Niño, warmer-than-average water extends throughout the central and eastern Pacific, changing wind patterns and influencing weather conditions worldwide. It has the potential to cause significant rainfall in the Americas, lead to drought conditions in Australia and Southeast Asia, and result in milder winters in certain regions of North America. La Niña represents the contrary, marked by cooler-than-average ocean temperatures in the Pacific, and it usually produces contrasting impacts. The patterns observed are integral to a natural cycle known as the El Niño Southern Oscillation, or ENSO, which has been taking place for millennia. Their impact extends beyond just weather. It also encompasses marine ecosystems, where temperature fluctuations affect fish populations and overall ocean productivity. Anticipating El Niño and La Niña enables communities to brace for their effects, including the management of water resources and agricultural planning. For millions of years, the planet has experienced periodic glacial periods. Throughout planet-living geosphere's history, the planet has undergone significant phases of extensive glaciation, referred to as glacial periods, during which ice sheets enveloped vast areas of the continental plates. The last ice age, concluding approximately 11,700 years ago, featured ice sheets several miles thick that enveloped large portions of North America, Europe, and Asia. At this time, global temperatures were several degrees cooler, and sea levels were significantly lower, as water was trapped in ice. Glacial periods occur due to changes in planet-living geosphere's orbit and axial tilt, referred to as Milankovitch cycles, which modify the quantity and distribution of sunlight that reaches the planet. These cycles function over spans of tens of thousands of years. During glacial periods, there are also brief phases of warming, known as interglacials, when the ice begins to melt away. At this moment, we find ourselves in an interglacial period. Glacial periods have significantly influenced planet-living geosphere's landscapes, sculpting valleys, forming lakes, and impacting the evolution and movement of species, including humans. The greenhouse effect ensures that planet-living geosphere maintains a temperature suitable for sustaining life. The gaseous envelope of planet-living geosphere functions similarly to a blanket, retaining heat and ensuring the surface remains warm. The greenhouse effect is crucial for sustaining life. The sun's rays penetrate the gaseous envelope and heat the surface of the planet-living geosphere. The surface subsequently emits heat in the form of infrared radiation. Some gases present in the gaseous envelope, such as carbon dioxide, methane, and water vapor, capture a portion of this infrared radiation and re-emit it in various directions, including towards the surface. This retains warmth, increasing the overall temperature. In the absence of the greenhouse effect, the average temperature of planet-living geosphere would plummet to well below freezing, approximately -18 degrees Celsius, making it impossible for liquid water to be present on the surface. The greenhouse effect is essential for making our planet a suitable place for life. Nonetheless, human actions, especially the combustion of fossil fuels, have raised the levels of greenhouse gases, intensifying the natural greenhouse effect and resulting in global warming. The equilibrium of these gases is fragile, and comprehending it is essential for forecasting future climate shifts, humanity, and the planet. In a remarkably short span of geological time, humans have significantly altered the planet. In the short span of our existence, we have made a lasting impression on the planet. We have removed forests, drained wetlands, constructed dams on rivers, and developed cities that extend across the terrain. we have cultivated plants and animals, transforming ecosystems to meet our requirements. Agriculture, originating around 10,000 years ago, converted grasslands into cultivated fields and facilitated the emergence of civilizations. The onset of industrialization in the 18th century significantly increased our influence, enabling the extraction of resources, the production of goods, and the consumption of energy on an unparalleled scale. Our actions have transformed the composition of the gaseous envelope, redirected the flow of rivers, and led to the extinction of numerous species. We have made our presence known in space, with satellites circling planet-planet living geosphere, and remnants from our endeavors scattered throughout near planet-planet living geosphere orbit. In geological terms, our existence is brief, but our influence is significant, prompting some scientists to suggest that we have entered a new geological epoch, known as the Age of Humans. Shaped by human impact, agriculture enabled civilizations to thrive. Agriculture's development marked a pivotal moment in the course of human history. Throughout the majority of our history, humans existed as nomadic hunter-gatherers, tracking herds and foraging for wild plants. Around 10,000 years ago, people in several parts of the world began to cultivate crops and domesticate animals. This transition, often called the Neolithic Revolution, allowed people to settle in one place, leading to the growth of villages, towns, and eventually cities. Agriculture ensured a reliable food supply, enabling larger populations to thrive and allowing some individuals to focus on specialized roles, such as crafting, building, and governance. This specialization led to technological innovations and the development of complex societies. Agriculture connected humans to the land, influencing cultures and economies significantly. Today, agriculture feeds billions of people, but it also poses challenges, from soil degradation to water use to greenhouse gas emissions. The narrative of human civilization is, in numerous respects, the narrative of our journey in cultivating food. Cities are hubs of human activity and innovation. For millennia, cities have played a crucial role as hubs of trade, culture, and governance. Today, more than half of the world's population lives in urban areas, a trend that continues to grow. Cities concentrate people, resources, and infrastructure, creating opportunities for economic activity and innovation. They are places where ideas are exchanged, art and culture flourish, and diverse populations come together. However, cities also present challenges. They consume vast amounts of energy and resources, generate waste, and can contribute significantly to pollution and greenhouse gas emissions. Urban areas are often hotter than surrounding rural areas due to the urban heat island effect caused by concrete and asphalt absorbing heat. Managing cities sustainably, providing clean water, sanitation, transportation, and housing for growing populations is one of the great challenges of the 21st century. Yet cities also offer opportunities for efficiency, as people living closer together can share infrastructure and resources, potentially reducing per capita environmental impact. The Industrial Revolution marked a turning point in human impact. Before the Industrial Revolution, which began in the late 18th century, human societies were largely powered by muscle, wind, and water. The invention of the steam engine and the harnessing of fossil fuels changed everything. Factories could produce goods at scales previously unimaginable. Railroads and steamships connected distant markets. Populations grew as food production increased and medicine improved. The Industrial Revolution brought unprecedented prosperity to some, but it also brought challenges: pollution, labor exploitation, and the beginnings of significant environmental change. The burning of coal, oil, and natural gas released carbon dioxide and other pollutants into the gaseous envelope. Forests were cleared, rivers dammed, and landscapes reshaped to feed industrial growth. The consequences of industrialization are still unfolding, from climate change to resource depletion. Yet it also spurred technological advances that have improved lives and expanded human knowledge. The Industrial Revolution is a reminder of the power of human ingenuity and the responsibility that comes with it. Connection and wonder. Planet Living Geosphere is a closed system, recycling its materials endlessly. Planet Living Geosphere is, in many ways, a closed system. While energy flows in from the sun and some escapes to space, the matter that makes up our planet is largely recycled. Water evaporates from the global ocean system, falls as rain, flows back to the sea, and the cycle repeats. Carbon moves between the gaseous envelope, global ocean system, rocks, and living organisms in the carbon cycle. Nitrogen is fixed by bacteria, used by plants, consumed by animals, and returned to the soil and air. Even rocks are recycled through the rock cycle, eroded, deposited, buried, transformed, and uplifted over millions of years. The atoms in your body have been part of countless other organisms, rocks, and waters throughout Planet Living Geosphere's history. This interconnectedness means that everything is linked, and changes in one part of the system can ripple through others. Understanding Planet Living Geosphere as a system helps us appreciate the delicate balance that sustains life, and the ways our actions can disrupt or preserve that balance. Every breath you take connects you to the planet's history. The oxygen you breathe was produced by plants and photosynthetic microbes, a process that has been ongoing for billions of years. Each breath links you to the tropical rainforests, grasslands, and global ocean system that generate oxygen. The carbon dioxide you exhale becomes part of the gaseous envelope, eventually absorbed by plants to fuel their growth. The nitrogen that makes up most of the air you breathe was released from volcanic vents eons ago and has been cycling through the gaseous envelope ever since. Even the water vapor in the air you breathe has traveled through countless cycles, falling as rain, flowing in rivers, evaporating again. Breathing is a simple act, but it ties you intimately to the planet's ecosystems and geological processes. It is a reminder that you are not separate from Planet Living Geosphere, but a part of it, participating in cycles that have sustained life for eons. The pale blue dot perspective reminds us of our shared home. In 1990, the Voyager 1 spacecraft, having completed its mission to the outer planets, turned its camera back toward Planet Living Geosphere from a distance of about 6 billion kilometers. The resulting image, known as the pale blue dot, shows Planet Living Geosphere as a tiny speck of light, barely visible against the vastness of space. In that image, every human who has ever lived, every civilization, every war and peace, every joy and sorrow, exists on that small point of light. The photograph, and the words of astronomer Carl Sagan reflecting on it, serve as a powerful reminder of our fragility and the preciousness of our world. In the vastness of the cosmos, Planet Living Geosphere is our only home, a small, vulnerable island of life. This perspective can inspire humility and a sense of shared responsibility for the planet, encouraging us to look beyond our differences and recognize our common humanity and our dependence on the Planet Living Geosphere. Exploration has revealed Planet Living Geosphere's wonders and its limits. For millennia, humans have explored Planet Living Geosphere, driven by curiosity, the desire for resources, and the need to find new lands. From the Polynesian voyagers who navigated the Pacific by stars and waves, to the expeditions that mapped continental plates and crossed polar ice, exploration has expanded our understanding of the world. It has revealed the highest mountains, the deepest global ocean system, the most remote deserts and jungles. For centuries, exploration has also shown us the limits of our planet, that Planet Living Geosphere is finite, that resources are not inexhaustible, and that our actions have consequences. The age of exploration connected distant peoples, for better and worse, leading to the exchange of ideas, goods, and diseases. Today, we have mapped nearly every corner of Planet Living Geosphere, and exploration has turned inward to understanding the complex systems that sustain life, and outward, to space. Yet the spirit of exploration, the desire to discover and understand, remains a fundamental part of the human experience. Planet-living geosphere is the only place where we know life exists. Despite decades of searching and the discovery of thousands of exoplanets orbiting distant stars, planet-living geosphere remains the only place in the universe where we know life exists. This makes our planet extraordinarily special. Life, in all its diversity and complexity, from bacteria to blue whales, from fungi to redwood trees, is a phenomenon we have found nowhere else. Scientists search for signs of life on Mars, in the icy moons of Jupiter and Saturn, and in the gaseous envelopes of exoplanets, but so far, the search has come up empty. This does not mean we are alone. The universe is vast, and life may exist in forms we cannot yet imagine or detect. But it underscores how precious, and perhaps rare, life is. Planet-living geosphere's combination of liquid water, a protective gaseous envelope, a stable climate, and the right chemical ingredients has made it a haven for life. Protecting this unique biosphere is not just about preserving resources for humanity, but about safeguarding the only known cradle of life in the cosmos. The beauty of planet-living geosphere inspires art, science, and wonder. From the earliest cave paintings to the symphonies of great composers, from poetry to photography, planet-living geosphere's beauty has inspired human creativity. The landscapes, the play of light on water, the colors of a sunset, the majesty of mountains, these have moved people to create, to express, and to share their wonder. Science, too, is driven by a sense of awe at the natural world, a desire to understand the processes that create such beauty. The more we learn about planet-living geosphere, the more we appreciate its complexity and the delicate balance that sustains it. Wonder is not just an emotional response, but a motivator for exploration and discovery. It connects us to something larger than ourselves and reminds us that despite all our technology and knowledge, the natural world can still surprise and inspire us. Cultivating a sense of wonder for planet-living geosphere is essential, for it fosters a desire to protect and preserve the planet for future generations. Protecting planet-living geosphere is a shared responsibility. Planet-living geosphere is our home, and it is the only one we have. Protecting it is not just the responsibility of governments or scientists, but of every person. The challenges facing planet-living geosphere, climate change, biodiversity loss, pollution, deforestation are global in scale and require collective action. Small actions, reducing waste, conserving energy, supporting sustainable practices, can add up when multiplied across millions or billions of people. Larger actions, policy changes, technological innovations, shifts in how we produce and consume are also necessary. The good news is that humans have shown the capacity to come together to address environmental challenges. The Montreal Protocol, which successfully phased out chemicals damaging the ozone layer, is proof that international cooperation can work. Protecting planet-living geosphere is about ensuring that future generations inherit a planet that is as rich, diverse, and beautiful as the one we know. It is about recognizing that we are part of the web of life, not above it, and that our well-being is inseparable from the health of the planet. Planet-living geosphere's resilience is remarkable but not limitless. Throughout its history, planet-living geosphere has endured and recovered from catastrophic events, asteroid impacts, volcanic supereruptions, glacial periods, and mass extinctions. Life has persisted, adapted, and diversified. The planet's systems have shown a remarkable ability to rebalance, to restore equilibrium after disturbances. This resilience is a testament to the robustness of natural processes. However, resilience is not the same as invulnerability. There exist critical thresholds past which systems might fail to bounce back, particularly within timeframes that hold significance for humanity. The failure of an ice sheet, the decline of a rainforest, the acidification of global ocean system. These events could initiate a series of consequences that may be challenging or unfeasible to reverse. Grasping the resilience of planet-planet living geosphere and recognizing its boundaries is essential for guiding our interactions with the planet. We need to recognize that although planet-planet living geosphere has faced numerous challenges, our choices today hold the power to significantly influence its future. The night sky overhead links us to the cosmos. Although this narrative has centered on planet-planet living geosphere, it is crucial to acknowledge that our planet is not alone in the universe. On every clear night, the sky above serves as a reminder of our position in the vast cosmos. Earth's satellite, our unwavering companion, formed from the very materials of planet-planet living geosphere. The celestial bodies, companions in orbit around the sun. The stars, far-off suns, some accompanied by their own planets. Our galactic home, the Milky Way, into the vast. Beyond numerous other galaxies, extending into the vastness of space, our planet exists within this immense universe, influenced by celestial dynamics. Earth's satellite's gravitational pull generates tides, the solar wind produces auroras, and asteroid impacts have shaped the trajectory of evolution. Gazing at the night sky can evoke a sense of humility, highlighting the vastness of the universe and the insignificance of our planet. However, it can also provide solace, linking us to the timeless patterns of the cosmos, to cycles that have persisted for billions of years and will endure far into the future. Each moment on planet-planet living geosphere contributes to a magnificent unfolding narrative. The tale of planet-planet living geosphere is dynamic, continuously evolving, revealing itself moment by moment. Volcanic vents erupt, rivers shape valleys, ice rivers move forward and pull back, species develop and disappear, and humans persist in molding the planet-planet living geosphere. This narrative is vast, covering billions of years. Every moment contributes to the whole. The air you just inhaled, the water cascading in a brook, the sunlight hitting a leaf, each one is a small thread woven into the grand tapestry of planet-planet living geosphere's narrative. Grasping this can provide us with insight. Our existence is fleeting, yet we belong to a vast and ancient continuum. The choices we make now will send waves into the future, influencing outcomes in ways we might not completely grasp. Recognizing this connection and our part in the continuous narrative of planet-planet living geosphere can motivate us to take thoughtful actions, to recognize the elegance and intricacy of our surroundings, and to ensure a vibrant, flourishing world for future generations. And so, esteemed listener, our exploration of the marvels of our planet reaches its conclusion. From the molten core beneath our feet to the thin gaseous envelope above, from the deepest ocean trenches to the highest mountain peaks, from the smallest microbe to the tallest tree, we have journeyed through a planet filled with remarkable diversity and beauty. We have observed the interconnections within planet-planet living geospheres systems, noting how the global ocean system, gaseous envelope, land, and life engage in a fragile equilibrium. The history of our planet has been meticulously traced from its tumultuous beginnings to the current era, a narrative inscribed in rocks, fossils, and ice. We have contemplated humanity's role in this vast narrative, the fleeting moment we have existed, and the significant influence we have made. Planet-planet living geosphere serves as our home, a planet that has supported life for billions of years. This world is a realm of marvels, brimming with enigmas waiting to be revealed, and splendors yearning for recognition. It stands as a delicate haven amidst the immense expanse of space, the sole location we are aware of where life thrives. This renders it invaluable. As you lie here, allowing your breath to settle into a gentle rhythm, envision yourself at ease on this extraordinary planet. Imagine the expansive seas, the majestic peaks, the limitless heavens. Experience the soft spin that creates day and night, the angle that ushers in the seasons. Listen to the gentle breeze, the soft flow of water, the quiet movement of leaves. The planet living geosphere has supported countless generations before us, and it will continue to do so if we take care of it. The narrative is ongoing, and as we inhabit this world, so too is our journey. As daylight transitions into darkness, each conscious thought softly succumbs to slumber. If you find yourself still awake, you may continue to relax, allowing the tranquility of the planet living geosphere to embrace you. However, if your eyelids are becoming weighty, allow the serenity of our world to embrace you and gently guide you into slumber. Gently close your eyes, take a deep breath, and let yourself sink into slumber, into tranquility, into the boundless and eternal embrace of the planet living geosphere that cradles us all. Sleep well, and as the final truths about Earth come to a close, I want you to take a moment to feel this very simple truth. The planet we live on is not in a hurry. Earth has orbited the Sun for over 4 billion years, experiencing ice ages, volcanoes, extinctions, and rebirth, and life continues, persistently and patiently. From that perspective, the fatigue of a long day doesn't feel so overwhelming. For me, Earth science is more than just geology or climate knowledge. It taught me a new value: learning to live in harmony with nature. The human body also has cycles, needing rest, just as the ocean has tides, just as forests need nighttime to recover. Understanding this, I stopped pushing myself to be constantly strong and allowed myself to slow down each night. It's also a form of gentle education, learning to respect my own biological limits. If these perspectives help you feel more at peace, don't forget to subscribe and stay with Sleep Science Top 1. On this channel, we transform science into accessible stories, helping you understand the world better, live a more balanced life, and sleep more soundly each night. Now, let the Earth continue to spin, and you can rest. Wishing you a peaceful night and a deep, natural sleep, just like this planet itself.